Hello, everyone. Welcome to the ARMA Future Leader webinar. It is my pleasure to introduce you to the speaker today, Dr. Pengju Xing. Dr. Xing is a research associate at Energy and Geoscience Institute at the University of Utah. Dr. Xing has over 10 years of working experience on geomechanics, both in industry and academics, in numerical simulations and laboratory experiments. His expertise is on enhanced energy extraction from subsurface with engineering treatment, including geothermal, unconventional oil and gas resources. He has experience in developing analytical solutions, numerical codes, laboratory experiments, and database methods related to various geomechanics applications. Without further ado, let's welcome Dr. Xing. And Dr. Xing, you can take over.
This is Pengju Xing. I'm from University of Utah, and I want to thank my colleague Kevin McCormick, Eric Edelman, John McLennan from University of Utah, and Dave List, Gregor Maxwell from Zephyr Energy. Today, I want to talk about the well stability analysis of wells in Paradox Play in southern East Utah, investigating on salt mobility. So first question, what is salt? Is what we eat every day? Yes, it is, but it's in the form of rock. We call it halite or rock salt. But its major component is same as what we eat every day. It's sodium chloride and HCl. So as we know, one of the most important features of the rock salt is it's easy to creep compared to other rocks. And here is a Paradox Basin. It's in Utah and Colorado, and the area we investigate is in Utah. So one unique thing of this Paradox Basin is that it has a setting of the salt class cycles. If you look at this figure, you can see this layer of salt, then followed by a clastic, another salt, a clastic, and repeating like this. So we talked salt halite before. So the clastic is composed of sandstone, siltstone, marlstone, etc. As well as usually where hydrocarbon form. So due to the unique setting of these salt clastic cycles, there are a lot of drilling programs. So here we invested the one well drilled in this basin, and this project supported by DOE, and some of funding is going into the drilling of this well. So we can see that there are drilling issues during drilling the well. So after 20 days of spot, there's drill pipe stock as 6,224 feet, and they start drill a sidetrack. The sidetrack means they drill another branch. But after the drill sidetrack at day 43, but only 2 days later, the pipe got stuck again as 9,273 feet. So after that, they drill another sidetrack, but finally they got a well blowout. Well blowout means the fluid come out from well, they can't stop it, and they have to pump a super hammer to secure well, and also they have to abandon the well. But then we do some analysis recommendations, and in just 30 plus months, they have successfully drilled another well, just 700 feet, 700 apart, and following our recommendations. So basically, there are 2 pipe stock incidents in this well, as I mentioned. So the first one is happening 6,000 feet. And the second one is deeper in around, it's 9,139 feet TVD. And they use 2 different mud weights. So first one is water-based mud, and second one is oil-based mud. And here we focus on the analysis second pipe stock in this talk. And there are three, so this figure shows the drilling of the during the second pipe start. So you can see the solid clastic, the layers, and the pipe start at solid 18, and we believe there are three mechanisms can contribute to the pipe start. The first one is borehole cream or shrinkage. The borehole shrinkage means the borehole size becomes smaller, and then it causes pipe stop. And the borehole shrinkage is caused by the soil creep. The second one is well bore breakouts. Well bore breakouts, like when under compression, and your breakouts, there's some small piece of rock fall into the well, and if it can jam the well and cause pipe start. And stall is for fracture slip. Somehow the structure, when you interact with the drilling, it can easily slip because of the pipe stop. So first, we can look at one of the drilling parameters during drilling. So it's the PVT total mud. The PVT total mud means the mud, they monitor the mud in the surface. So ideally, you circulating the mud, you should gain too much or lose too much. But here, start from 8,700 feet, you start gain a lot of mud, means something happened. So presuming the calibration is urine, the marking may suggest the borehole shrinkage. The borehole becomes smaller, then squeeze the mud out. So they can, like, due to the creep, or can also another reason you enter the zone with some fluid, like come out. So, but creep is very is one of the reasons they call this. Here is one 1D very simple 1D analytic solution. You can calculate the borehole shrinkage. So the R is current radius. The R0 is the original radius, and here is related to your creep. And so the AB, so N the related to the salt properties. A is so B is related temperature, N is related stress. The delta is creep time. So this sigma is incident stress, and PW is wellbore pressure. So basically, you can calculate how much your well will shrink based on these parameters. But first thing is you have to determine the constants ABN that are related to salt properties. But we don't have any core samples in this well. But fortunately we have lab creep tests for the cores from the nearby wells. We have two samples. They done the creep test. So here's how here's some data from the one of the samples. How is the creep test is done? So basically, first you apply a 600 psi confining pressure. Then you do multiple cycles. So in the first cycle, you increase axial stress from 600 psi to 1,100 psi. So then in a very short time, so the stress difference is 500 psi. Then you keep this constant, the stress constant, and wait until wait for 20, then monitor 24 hours for the strain change. And in the next cycle, so increase axial stress from 1100 to 1600, and then wait another 24 hours and repeat. So we have this from stress difference from 500 psi to 4,000 psi. So you got this data. So the creep string can be expressed as like in this like this. We know the string rate, we know the stress, and we know the temperature when we did the experiments. And AB, I just copied from the reference, and the only one thing we can calculate is the N, the stress component, and it's you see it's power law, so it's very sensitive to this, but we can calculate it based on this experiment data. Okay, then we substitute these parameters back into this equation, and with ABN, so N is related to your stress different level, and because we have different different stress difference level, so we calculate the N based on this stress difference. We just do some interpolation, and also the temperature here is the reservoir temperature. It can reach to 170 degree F. So after you substitute all these parameters in, what you got is like the current wellbore radius is only 90% of the original one. So it can shrink from 8.5 inch to 7.6 inch as this 9,000 foot TVD, so 10% shrinkage. So this could result in the pipe stop. And if we go back to this the chart I showed before, and we see that there's about like 60 barrels mounted, and I calculate the volume. Like if you 10% of radius shrinkage will cost the 19% fluid push out surface, which is around 40 barrels. So yeah, just similar to just cross validation each other. Okay, so next, if I set threshold like if you have 10% shrinkage, you have a problem, then what is moderate you need to prevent this 10% shrinkage? So this chart can answer this question. So this solid line is like the creep, the mud weight required at different temperature level. So the higher temperature, the severe the creep, and what the red one at the real temperature at 9,000 feet is 170. So the blue line is 170 degree F. So the required. So this is the required, and the dashed line is what it actually used. So the actually used at this around this 9,000 foot TVD is 13, but it is required in the blue line. Is required here is like 13.4, so it's lower. It's lower than the required required value, and so that's why this could cause a problem. Okay, so the previous one is the analyze based on the creep, the equation, the data, the lab data, and next we have also have a lot of data from the nearby wells, offset wells, and we have here's so the creep, the amount of creep is related to actually the mud weight. So if you put your more mud weight, actually you have more support, then you have less creep. So we have this data, and also we have the caliper data. So the caliper data is, so when they finish the hole, they put a tool down hole, they can measure the size of the borehole. And here is plot here. This plot is the vertical axis is the ratio of the so the borehole size over the drill bit. The drill bit is like the size of the drill bit is the original size. So you drill it in original size, but because due to some reason, the actual size, like maybe due to creep, actually is smaller. So the R0 is the base size also is the original size of borehole, and R is current one. So, and this is the vertical axis. The horizontal axis is dimensionless stress difference. So this is related to your in situ stress and the model weight. You make it dimensionless. So the larger the stress difference, the dimensions value is larger, the creep could happen. And you can see that as you increase the S, you can see a clear trend, the borehole is reduced in the size, And for the nine of the wells, we have this data, 7 of them like show this size reduction. You can see I put this 7 of them here. They all like once the S exceed some value, they all have a reduction of the borehole size. It's highly due to the creep. Okay. And we say like if you set criteria, say like we don't want this size reduction, and we want this as smaller than 0.6, and then we have this plot, the minimum amount of weight to like you keep your S smaller than 0.6, and then the 9,000 foot TVD. So the required amount is 13.2, and it's like, remember what we calculated before is 13.4. What we actually use is 13. So it's not like, so the used value is not too much low than the required, but still it's lower. So if you consider the uncertainty, it could give you some problem and cause the borehole shrinkage and stuck your pipe. And so yeah, the next one is another possibility is a breakout. So you look at this figure. So under the compression, so these breakout happen. The small piece of the rock could fall into the hole and jam the hole. And so, but it's a salt. It's pretty ductile, right? But salt is also have a low strength compared to other rocks. So UCS, we measured in the lab is only 3,600 psi. In typical rock, you have like close to 10,000 psi. So it's relative low strength. So it could happen. And then we calculate what about the breakout angle. The breakout angle means this angle. So this angle is larger. The angle means the more severe the breakouts could happen. So we calculate the breakout angle. So here with two scenario, with two different build coefficients. So one is 0.3, another 0.4. So this typical value of this kind of rock. And it's very sensitive to the build coefficient. And if you increase the 0.3, the breakout width like around 70, 80 degree. And if this breakout build coefficient 0.4, it could increase 100. So so we set a failure threshold of 75 degrees. So if the breakout width is greater than 75 degrees, it could be a problem in water well, and 60 degrees for horn well. The horn well has a lower threshold because in the horn well it's difficult to carry out all the fittings out. So it's more difficult. And so again, if the breakout build coefficient 0.3, the critical model weight is around 13, so around 13. But if you consider some uncertainties here, it's still kind of you want to put your model weight higher than this, so keep it safe. Right? So, and third reason is slip or fault. And here we can see that there's some fractures intersects with fracture of fault, intersects with infer from seismic data, intersects with the well. And my colleague Kevin McCormick applies this chart. And so the triangle here is represent these azimuths of these fractures, and it's in the more dangerous zone, right? So it's if you coincidence with a more high pore pressure zone, it's easy for these fracture to slip, right? So yes, let's come to conclusions. The three mechanical salt creep, well breakouts, and fault slip are all potential individual collaborative contributors to the well stability experience and experienced in the stack pipe incidents. We don't know which one, like, to be honest, we don't know which one is a real reason, but we believe all these three can be or like individually or collaboratively. We just don't know. So we put all the things together. But the important thing is that all these three failure mechanisms are all associated with lower model weight. So analysts assume that the minimum required model weight is above 13 ppg, so pound per gallon, and the actual use is 13. But you have to consider the uncertainties of all these analytes, right? So, and we recommend the increased model weight to 14 pound per gallon as deeper location, and it will mitigate the risk of the well instability, because if you increase model weight, you have more support, your ball shrinkage will reduce, and the breakouts can be reduced as well, and the prorated force slip can be reduced. So our recommendation is that for them is drill head, like pull back and forward. You cannot drill too fast. I mean, you drill some little bit and pull back, and make sure it's not stuck. And watch the change the weight on bait and torque spikes always. And what the important thing, watch mod with gain loss. It's rapid gain, increase mod weight. Yes, as I mentioned, what's gain intake? It either means the squeeze the borehole is the creep, or you encounter localized hyperpressure zone is also can cause you full slip, right? And careful communication with the MPD vendor. MPD is manage pressure drilling, and weight up as appropriate. And like 13, 12 is not high enough. Yes, thanks for the support, DOE, and thanks for the colleagues. And thanks also for ICON. Yeah, thank you.
All right, thank you, Dr. Xing, for this very nice presentation. We have a question in the chat from UPRAS. Would you like to unmute yourself and ask, or you want me to read out the question?
Yes, my name is Umesh Prasad, just by the way.
Okay.
My question was, in the salt, sometimes we see dissolution. In one of the two wells, you mentioned one was drilled by water-based mud and the other one
Yeah,
well-based.
so
was there any dissolution instead of shrinkage or creep?
Very good question. So in the first pipe stop, we don't, we think it's used word-based model. So we think that because the circulation rate is low, so we assume that when you dissolve the salt, it's some of the part, so because it's not, so it's like it's not, it's the only uniform is salt, like it's salt, it's salt crusted. So in the boundary, there's maybe some piece of rock falling into the hole, so called this stock. And
That's
it
fine.
has a
And
low circulation rate, and it's don't have may not have enough power to carry these cavings out. So this probably the reason for the first stop.
yeah, and very another quick question that
Cavings.
also I put in the chat was, in the conventionally in the lateral section, for example, Mark Jobek book, he considers the threshold level of breakout as 30 degree, but you assume 60 degree. Was there any reason that you may be able to evacuate those breakouts or cuttings? Why did you use 60 degree instead of 30 degree?
You mean in Zobac's books is 30 degree?
Yeah, usually, or petroleum geomechanics says in the vertical well, your threshold should be 90 degrees, but in lateral 30 degree. But in your statement, I read
Yeah,
some.
I think
Yeah,
I got it from somewhere. I don't remember. I
yeah,
don't remember the reference. Yeah, they got 60 degree. Uh, yeah, I just don't remember what's the
that's
reference.
too high. That's too
But
high. It should be lower. Yeah, okay, that's fine.
yeah, 30 degree, you mean the whole thing or the half? Whole
No,
thing is
in
30
the
degree?
lateral section, because you cannot evacuate the cuttings efficiently, there is always some inefficiency. The
Mm,
threshold level of breakout is considered much lower, only 30 degrees.
okay.
And in the vertical section, 90 degree, you can evacuate easily. So
Mm-hmm.
that is the rule of thumb, but it's not absolute, so it's okay.
Yeah, yeah, it's just like yeah, if it's 30 degrees, then you have more problem. But
Mhm.
yeah,
Okay, good, thank you.
thank
Otherwise,
you.
very nice work on the salt, yeah. And by the way, did you
Yeah,
use isotropic stress condition in the salt? Did you use isotropic, like vertical, horizontal, all are
yeah,
equal?
isotropic. Yeah, yeah. 1D, only one direction. Use the
No, one day, I mean,
maximum.
SH mean, SH max should be
Is that
almost same as overburden.
yeah, actually because it's salt, right? It's kind
Yeah.
of where it's close. SH and SH max very close to each other, and it's almost the same as
Okay,
our
good,
estimation. Yeah,
good, good. Thank you.
yeah.
All right. Anyone else? Just feel free to unmute yourself and ask a question.
Yeah, so nicely is that we have this data available. So it's a simple 1D solution. And yeah, if we have time, we can do some simulation to make it more complicated. Yeah.
All right. So Dr.
I
Xing,
do
I
have a
have a,
question here. This
oh, sure,
this
go
is
ahead.
Mohammed Azimuddin from Chevron. I was wondering the direction of the whole ovality. Is there any specific orientation since it's an isotropic situation? I don't know which particular direction do you have an ovalized hole in the situation where you have isotropic stresses. At least the two horizontal stresses are isotropic.
So the we have a colleague like so here's his estimation of the stress. He thought is actually it's what it's the strike slip. It's strike slip. So but all these three are very close So the overburden hydrogen mass and hydrogen mass are very close to each other. It's not too much difference. And maybe it's different. I mean, in the caustic and salt, it may be different. But yeah. So we have a colleague who investigates this. But still, he believe like one is a stress slip. Another thing is that these all these three are very close to each other. For stress. Is your question?
Now that I'm looking closely at the stress gradients, they are close. They're not totally isotropic, but they are
No. They are
slight
not.
differences. So
Yeah,
you would
they're
expect,
not. We put a little bit difference.
yeah.
But actually, you don't know. It's difficult to measure the SH max, right? So it's only yeah, it's only his guess. I mean, we have a measurement of the SH mean. It's 1.02 is high, and the pore pressure is high. But the SH max,
Yeah.
usually you cannot measure that. He just put like 10% more.
Yeah.
I guess. Yeah.
Mhm. And what is the basis for the Bios coefficient of 0.3?
I think
Is that something measurement or is that estimation?
no, it's not measurement. It's from some reference. It's between 0.3 to 0.4 for halide.
Okay.
Yeah.
Do you have the reference handy here, or is that part of the paper or something? I can find it.
Yeah. Let me show you the paper.
I second question from Ajim. This is Umesh Prasad. You are one of the experts, so that's good. Let's find the good reference. Yes.
Yeah, the reference. Let me see.
I can look up that paper.
Yeah,
actually.
you can look at this reference. I just read Jaden's
And just for my clarification, was this paper presented at the last meeting in Golden?
yeah. So
Okay.
you can find in this reference, maybe this one.
Okay. Sure. Okay, got it. Thank you.
Yeah. I presented in the similar thing in Golden. Yeah.
Yeah, I may have missed that because there was so many. I
Yeah,
was
so
there,
many
but
sessions.
I didn't.
Yeah.
Yeah.
Hi, Pengju. I have one question. When you calculate the Mach density for variable stability for maintaining to prevent the variable collapse, what kind of model you use? Because this salt has a strong viscoelastic or viscoplastic performance.
Yeah, just like
Yeah.
elastic model.
Yeah, but
So
do you think
if
that
you
will be
got the Zobax books, you can find it. I use the icon to calculate.
Yeah,
Yeah.
but my concern is like
They do not consider any viscous in
right.
this
But
breakout calculation.
if you consider that, then it might significantly change your Mach density to maintain variable
I know.
stability.
Yeah. So it's elastic calculation. So so that's why so it's so the UCS is low, but it's very ductile, right? So it's still like it's maybe not that easy to get a breakouts.
And you also have like a transient property change of your soft rock, and maybe the longer time you drill, your safe mud window is actually shrinking all the time. Or expanding all the time. Yeah.
Mm-hmm. Yeah, that's why.
But how do you like incorporate this factor in your estimation without the like including this viscoelastic property in your modeling? Because you have a
Yeah, I
lot of
can.
field data. Yeah, you have a lot of field data, but did you do some like calibration or some other ways to incorporate this factor?
No, we
Okay.
don't.
Okay.
Yeah,
Okay.
so this variable stability, because the very basic elastic
Right.
calculation,
Yeah.
it's not necessary to be real.
But
So if you have a
yeah.
better model, you can try to calculate.
Yeah, but
Um,
a task should have some software that to capture like a plastic or viscoelastic constitution or
yeah, yeah,
behavior of the rock.
yeah, sure, sure.
Okay.
Um, yeah, I think there's
Okay.
still a lot of work to do.
Yeah. Thanks. Yeah. That's great.
But
Yeah.
the good thing is that the increased mod weight and this successful re-drill another well 700 feet apart. They don't have
Yes. Yeah.
they don't have the stop pipe issues in the well drilled in June,
Yeah.
last several months. Yeah.
Okay. Yeah.
Dr. Xing, I have a question about the mechanism behind this creeping. Do you know if it's like a brittle creep or is it like pressure solution that induced the creep?
So what do you mean the pressure reduced creep?
Pressure solution. So if you put something that's soluble
Mhm,
in water and then you apply a lot of pressure, like
mhm.
combining stress and so on, there's like a thermodynamic effect that the solubility will actually increase. So even
Oh,
the
no. It's oil-based mud, so it cannot dissolve the salt in a second.
right,
So they changed the mud type from after this, they changed mud type
yeah,
from because they start to enter the salt. So
uh-huh,
above 6,000 feet is major is not non-salt there. But salt one is a first salt formation they entered. So, but they got stuck here. But after that, they changed the mud from water to oil. So
okay,
you have very little dissolve. Yeah, you cannot dissolve that too much salt during this
mm-hmm,
during this second pipe stock.
I see. So the gripping mechanism you see here is mostly like brittle grip, or
Brittle?
yeah,
Yeah, it's still for me to imagine. So it's like
right. So for example, in the grip model you use on slide 7,
mhm.
what is I'm just trying to figure out what is like the creep mechanism. Is
Uh,
that
let me find this paper. So let me see here. Let me stop a while. Please let us discuss.
it could be a empirical model. So it
Let me show you this paper.
I see.
Okay.
Hmm. Not creep. Okay.
Salt creep calculation. Okay.
Hmm.
Um,
Yeah, that's it.
hmm.
Dependent on temperature, differential stress, confining stress, grain size. presence of inclusion of free water, free gas bubbles.
Basic static plastic
Static plastic
storage
theory. Okay.
with finite element techniques, right?
Mm-hmm.
I have
Great. I see. I think this is like more or less empirical, right?
yeah,
Oh,
there's another
there's
paper.
yeah,
They
reference
show how
5.
to derive these equations.
Okay, cool. I
Better
can check
one.
this out later. Yeah.
Yeah.
Yeah, great. Thanks.
Do you see this one, this paper?
Yeah. Yeah, so it's a power law grid model. Yeah.
See this? This how the Xing shape, okay,
Mm-hmm.
create create
Yeah, I think they fit in a power law. Yeah.
yeah here,
Mm-hmm.
right?
Okay.
Maxwell model, right?
Yeah.
Yeah.
It's a spring and slider.
Mm-hmm.
No. Yeah. A spring
This
and
one.
dashboard. Yeah.
Yeah.
Okay. Cool.
Mm-hmm.
Thank you.
Yeah. Okay.
Yeah. Do you have other questions? Oh, I see Peter here.
Peter. Yeah.
Yeah. Yeah. Thanks for
Nice
joining
talk.
us,
Yeah.
Peter.
Yeah, I'm here. I'm sorry, I missed the very first part. I'm not sure why, just Zoom wouldn't let me in, but Wei sent me another link and I got in. So I want to thank you. That was a very interesting talk and glad to see so much commentary afterwards.
Yeah. Very good comments, good discussion. Yeah.
Yeah, I think these future leader webinars are terrific. You know, they're very informative. They bring everybody up to speed on what you're doing. I think it's one of the nicest aspects of ARMA.
Yeah. To be honest, I like this small group, so I had more discussions. Yeah.
Yeah, sometimes mainly because you know, they're not small by design. They're just small because the audience is limited to ARMA members.
Yeah. Yeah.
So it's
Okay.
really a benefit of ARMA. So I think the discussion always reflects that, and that's good.
Mm-hmm. Yeah.
Great. Yeah, so if we don't have other questions, I would like to close the session. Thank you so much, Dr. Xing, and we will meet in 2 weeks.
Mm-hmm.
All
Thank
right.
you.
Yeah.
Thank
Thank
you
you,
all.
everybody.
Bye.
Have a good day.
Thank you.
Thank you.
Thank you.